Hello, everybody. How are we doing? You guys have any questions before we get started?
Yeah, for the recordings of the classes, where can we find those?
Right now, they're just on YouTube. I haven't posted links, but I can do that right after class. Do you guys think that would be helpful? Okay, yeah, I can do that. It takes a little bit of work to get all the links set up, but I'll try to get them up at least the day after we do class. So I don't think I can promise the same day, but the next day I can do it.
Thank you.
Sure. Anybody else? So let's see. Today we're only covering one section. I've kind of tried to group the easy sections together because this is sort of a compressed class in the summer. You know, there are some days we have to cover multiple sections, so I've tried to put like the easy sections together and spread out the harder ones. Like yesterday, I kind of had to lump a bunch together. So your homework from yesterday is probably a little bit longer than it is in some other sections, but anyways, the things that you have to turn in by the end of today. So remember, these are always by 11 p.m. are the solutions to those summary sheet problems, and then these three WebAssign sections. Okay. Was everybody able to get a good bit of that done yesterday? Good. And just a reminder, I can put this reminder on there. There's going to be some help sessions today if you haven't gotten everything finished. So I'll be available from 3 to 4 p.m. and then 7 to 8 p.m. Help sessions. So right after class, I'll be available for an hour and then 7 to 8 tonight. Okay. And then let's see. So yeah, any questions about any of that stuff? Nope. Okay, well then let's jump right into the new stuff. So if you watch the videos, you'll notice that today was basically about, well, in my mind, it's kind of three things. It's basically exponential functions, which we talked a little bit about before. But then there's kind of two other things. There's logarithms, which are always kind of intimidating the first time you see them. And then there's these things called inverse functions. So we're going to try to kind of tackle these things today. And I'm going to kind of skip the part on exponential functions because, you know, we all kind of know that an exponential function, right? Maybe I'll just write it. Just to remind everybody that an exponential is something that looks like a number to a variable power, where the base, which is what we call the a, should be a positive number. Okay. Okay, so that's an exponential function. Now, you know, very often when you do something, like in the real world, you want to be able to undo it, at least in a lot of situations. And in math, that you also kind of want to have that property. So, you know, there are some things that you can undo and there's some things that you can't undo. So like, you know, like in the real world, like maybe you can fold a piece of paper in half. That's something you can undo by unfolding it. But if you took like a metal soda can or something and you just smashed it, that's very hard to put back into the, you know, the form of a metal can, right? You have to do a lot of work to do that. So it's kind of the same way with functions. There are some functions which you can undo and there are others which you can't. And we're We're going to kind of explore that today. So the main idea here is if we have, try to write better. If we have some function, so for functions like f, or you can think of it as f of x, f is sort of an operation that does something to the number x for various numbers x, right? So if you want to be able to undo that operation, so that would be saying, if I give it a number x, so you can sort of think of it like x gets transformed somehow into f of x, then I want to have some operation that undoes that gives me back to x, right? And this part will be called the inverse function, the one that undoes whatever the original one did to x. That's going to be called the inverse function, and there isn't always one, and we'll talk about when there is and when there isn't. Okay, but let me go ahead and give you the definition of just what an inverse function is, the proper mathematical one. So if we start with some function f, like we had before, then maybe we come up with something we think that undoes it g. And so if we think g is the inverse function of f, how we would actually check that is we have to say that, well, if I take my number x, I feed it into f, and it gives something out, and then I feed that back into g, you know, it's like in this picture up here, like, you know, when you go from x to f of x, you've plugged x into f, and then here we're trying to say, if I plug it back into g again, what should come back out is x, right? So I return to what I plugged in originally, right? F did something and then g undid it. But it also has to work the other way. So if you feed your number into g, g should also undo f, or f should also undo g. It should work both ways. So you have to have it go in both orders, f first or g first. Okay, and this, if a function g satisfies both of these things, then it is the inverse function. Okay, and there's a special notation for that. So if there is an inverse, there is only one of them. So there's only one way to undo a specific function. So instead of calling it g, we usually will call it f to the negative 1. Or we could just put f to the negative 1. We don't need the x. But just a warning. So, you know, this we would read as f inverse. But, so this is just like a big warning. F inverse is not the same as 1 over f. So you might think like to the negative 1 power means 1 over f, but here that doesn't. So you have to be a little careful about the notation here. I mean, there is one special case where this is true. But yeah, but usually it's not. Okay. So this is the definition. But let's think about it. So this is sort of how it works in equations. Let's think about how does an inverse work graphically. So let's think about this graphically. Nope. This one. Okay, so I'm going to draw two graphs here. And one function will have an inverse and one won't. Okay. So in the first one, I'm just going to draw something like say this. That'll be my f of x. And in the second one, maybe it does something like this. So let's say that's like g of x. Well, let's not use g because we just used g before. Let's call it h of x so we don't get confused. Okay, so an inverse function, remember kind of the idea is if I take an x value, then I plug it into f and it gives me an output, f of x, right? If there's an inverse, then it should have the property that if I plug f of x into f inverse of x, I should get back to where I started, right? Okay, so essentially what that's saying is that in this picture, what we did is we went up and then to the left, right? But if you think about it the other way, that's what the inverse would do, is it does it backwards. It would say, if I take my output and use that as my input, and then figure out what input that would have gone to, it has to come back to where it started, right? And you can do that, this sort of picture here, for any x value, okay? And so the idea here is, well, I'll tell you in a second, but let's look at this other one, because there's something that goes a little bit, that can go a little bit wrong. So if I choose an x value like here, well, okay, I'm fine. I got an f of x out, right? But if I want to go backwards, let's suppose I hadn't drawn these original lines. If all I knew is that I started with this number, f of x, and I didn't know which x it came from, to figure out which inputs it would have gone to going backwards is there's two of them, right? There would have been this one and this one, okay? So this is an issue, right? Because if you want something to actually be a function, whenever you plug one number in, one other number has to come out, right? And this would tell me that two different numbers come out. So this wouldn't actually be a function, okay? And so what's going on here is there's this property about what is called one-to-one. So the first function is one-to-one. For every input, x, there's exactly one output, f of x. But in this other picture, this is not one-to-one. Okay, because this one, if I choose one input, or sorry, I'm kind of saying it backwards, but if I choose one output, f of x, there are more than one input that makes that true, right? There's like an x1 and an x2. Okay, so we're not going to go like into deep detail about like one-to-one means, but it, basically what it means is so one-to-one functions have inverses, and ones that aren't do not have inverse. Don't have inverses. And the quick and dirty way to tell is what's called the horizontal line test. So if you want to figure out whether a function has an inverse, what you do is you take your picture. Let's draw maybe another picture. You take your picture of your graph, and so say it looks something like this. And you imagine there being like horizontal lines. So if I can draw any horizontal line, so like this one, when I draw it, it doesn't touch the graph at all. If I draw one like down here, where it just, like let's say hits the graph there, that one only hit it once, and that's fine. But if I draw one in the middle here anywhere, it'll hit the graph multiple times, right? So if you can ever draw a horizontal line that hits the graph multiple times, that means it's not one-to-one. So if any horizontal line touches the graph more than once, it's not one-to-one. And if that doesn't happen, then it is one-to-one. Touches the graph more than once. Once it is not one-to-one. Okay, so that's the basic idea. And we're going to just concentrate on a few specific examples. Like I'm not going to really, like we're not going to spend a whole lot of time thinking about inverses in general. We're just going to look at the inverses of a couple like key functions. And so the first one we're going to look at is the logarithm. Okay, so if I start with the exponential function, and I ask the question, does this function have an inverse? So maybe let's use b to the x. I think the book uses b, so let's try to stick with b. B for base, where b is a positive number. And so remember, if b is bigger than 1, what does the graph look like? So let's, we could do something like 2 to the x. Well, 2 to the 0 is 1. And if I go over to like 1, 2 to the 1 is 2. And it keeps going up. So this is not a point. But if you remember, it looks something like this. Okay. And this does pass the horizontal line test, right? If I draw any horizontal line, it only hits once. Or if you draw one down below, it doesn't hit at all. Both of those are fine. So this is one-to-one. So it has an inverse. Okay. So there is some operation that undoes exponents. And that inverse is called a logarithm. It's just another new operation that if you haven't heard of it before, is just a new thing. But let's see. So let me write this out properly. The inverse of the exponential is so the inverse is denoted like this. You put log, and then you put the base as a subscript. And so this is called the log base a of x. Okay. So you would read this as log base a of x. Okay, and that's just what we call the inverse. Like we just gave it a name. okay? And remember, what do inverses do? They undo the original thing, right? So this new function, this log base a of x, has the property that it undoes exponentials. Okay, so what does that mean? It means if I take an a to the x, and then I apply my logarithm with the same base, I plug that in, that should undo the operation of, putting x in the exponent, and it just gives me back x. And it also has to work the other way. If I start with the logarithm, base a, and I put that in the exponent of an a, right? So there's kind of two operations. There's, the first operation is you take your x and you put it in an exponent, and the other one is taking the logarithm. And so here now I'm taking the logarithm first, and then I'm putting it in the exponent, and that still has to become just back to what you started with, okay? Okay. Now, when we were talking earlier, like when we talked way back up here, when we were first thinking about inverse functions, right? We had this picture where we said if we started with an input and then got the output, the inverse does the opposite. It has, instead of, it takes basically the original output and uses that as the input, and gives back the original input as the output. Okay, so what that means in terms of all this stuff is, so what we were saying is, let me just write it like this. Inverses swap inputs and outputs. Right? Whatever was the input is now the output, and whatever was the output is now the input. Okay, and so what that means in terms of a graph, okay, so if we have our original, so say this is a to the x, and I have a point on here, this would be, let's say x comma y. There's some x, y coordinate there. Then what the inverse is going to take it to is it's going to swap them, and it's become y comma x. It's going to swap the inputs and the outputs. And so what it turns out that does is, is if you draw the line like y equals x, maybe I should make this a dotted line. So if you take the line y equals x, and you take your original graph and you flip it over that line, that's exactly what it's doing, is it's swapping x and y, and you'll end up with your graph of your inverse. Okay, so the new graph will end up looking like this. It should be somehow symmetrical, maybe it's kind of close. And so this other one will be called, this will be the log base a of x. Okay. Okay, so that's one thing to keep in mind, is that inverse functions, if you want to figure out what the inverse looks like given the original, you flip it over the line y equals x. Okay, so I'll pause. Are there questions so far? Okay. Okay, so let's start getting into like the nitty-gritty stuff where we can actually calculate things. So let's talk about calculating with logs. and then I'm going to have you do some work with it. Okay. So one way of thinking about logarithms is if you start with, okay, so basically what we're interested in is like, how do I actually figure out if I take log base, let's stick with B, try to stick with B everywhere. How do I figure out what this number actually is if I plug in an X? So what you do is you call it a number Y, and you think about it in terms of the inverse. Let's just write it in words. So this means the same thing as, well, the idea is if I raise both of these, or I put these both in the exponent of A, or sorry, B, you get B to the Y equals B to the log base B of X. But remember that these two undo each other, right? B raised to a log base B, those cancel basically. And so what you end up with is this. So like these two things are interchangeable, these two statements. Okay, and so the way to think about it is, if you want to know what log base B of some number is, your goal is to figure out what number do I put in the exponent of B to get the thing I plugged in. And so sort of a quick thing I use to remember it is, like, let me just show you an example. Say we want to know what log base 4 of 16 is. Okay, so I mean, the way I was doing it up here, you would set y equal to log base 4 of 16, but that's the same thing as asking 4 to what power y is 16. Okay, can anybody tell me what y would make this work?
2.
Yeah, so y has to be 2. So this is equal to 2. And kind of the way I remember it is, like, if you just look at the log that you're interested in, and you just ask, like, what exponent would I put here so that you could, make this equal? And that'll be your answer, is whatever you fill in that blank with. Okay. Let's see. Okay, so I've given you a fair amount of information, and there's more on the summary sheet I'm going to show you. So let's see. So if you go to our Canvas homepage and you go to week 1, and you go down to, so you can either go to Thursday. Yeah, just go to Thursday, the Thursday checklist, which is not apparently what I clicked on. Also not what I clicked on. Okay, there we go. It's being a little slow today. So if you go down to the worksheet section, this is going to be one of the worksheets you got to work through, and you go ahead and open it. What you'll see is it kind of has a summary of the things I've been saying. It has some of the definitions I've been telling you. Oh, and yeah, there's one more thing I should tell you. And it has these. Okay, so before I tell you about that, let me tell you one other important thing. Kind of the last thing you need to know before you can try some of this on your own is we were talking the other day about this special number called e, right? So it turns out, that this is a very common way to use with logarithms as well. So the natural log, it's just a special one where you put e as this base. Okay, and just because it's so commonly used, instead of writing log base e of x all the time, we give it a special name. So we call it just ln of x. Okay, like log natural, though I don't know why it's reversed, probably to emphasize that it's a logarithm, or it's the logarithm of the natural constant e. Okay, and so yeah, it's just, this is just one definition, but this is the one we're going to use the most often. Okay, and so if we go back to this worksheet here, it has all these properties, right? Just like you have all these properties of exponents you have to learn, there's sort of the opposite properties of exponents, right? Because that's the inverse function. So there's all these ones for the natural logarithm here. Okay, and what I'd like you to do now is I'm going to put you into groups again, and I'd like you to work through exercises 1 through 3 here on this sheet together. And you might have to look at these, right? Because I don't really have time in class to talk about each one of these individually, but just see if you can unravel them yourselves, and I'll come and help you. And also I have our TA will also come by and help. Okay, so do you guys have any questions before I throw you into groups? Alrighty, well let's do it then. Let's see how many of you are here today. Just about everybody. We'll do 5 groups today. No, we can do 6. Alrighty, great job everybody. Welcome back. So were there any questions about those questions 1 through basically 1 or 2, I guess?
I have a question about 2A. We were going over it, and then I think the answer got cut off right when we jumped.
Oh, okay.
Right, so I was just wondering, is the answer t equals ln 100 over 7?
Let me look. Yes.
Okay. Cool.
Yeah. So yeah, one thing I didn't mention, but that whenever you're trying to solve an equation that has a variable and an exponent, the only way to really get that exponent out of that variable out of the exponent is to take the natural log of both sides. Right? So that was kind of the technique there. And then the natural log cancels the exponent, and you're just left with something you can solve by the usual algebra. Okay, any other questions? Okay, so that was kind of your crash course in logarithms. Now comes the crash course in inverse trig functions, which are not everybody's favorite thing in the world. But we're not gonna, mostly I just want you to be aware of the very basics of inverse trig functions. So let's talk briefly about those. So, the logarithm was the inverse of the exponential functions. You can also ask, like, what are the inverse of like trig functions? But the problem is if you take a graph like sine, So if you take, say, sine of x, well, we said that a function only has an inverse if it passes the horizontal line test and it's 1-to-1, right? This one is not going to pass the horizontal line test, right? Because it keeps going up and down, right? So any horizontal line I draw in the middle here, you know, if I drew one in here somewhere, it would fail, right? Because it hits multiple points. So these are not 1-to-1. So how can this have an inverse? Well, the trick that people use is they say, well, it doesn't have an inverse everywhere. It only has an inverse of a small part of it. And so what we do is we erase like all this part. We erase all the part that kind of wrecks it. So we get rid of all this. And we say, well, with the part that's left, okay, so let's make sure we know what all these values are. So this is pi over 2 and minus pi over 2. This y value is 1. This y value down here is minus 1. So this is a piece of sine of x. It's the piece that's only between minus pi over 2 and pi over 2. Because if I erase all the rest, now this passes the horizontal line test. It's 1-to-1 on this piece of it, right? Now it has an inverse. So if I take the inverse of this, you know, you basically switch the inputs and the outputs, right? And the way I tend to think of that is I have a hard time visualizing like what it means to flip over the line y equals x. So instead what you can do is you can do it a rotation. You can rotate it clockwise 90 degrees and then flip it over the x-axis, and you can get the right picture. So basically what happens is, like this point here, instead of being, so here it's pi over 2 comma 1. In this picture over here, it'll be 1 comma pi over 2, right? So it'll be like somewhere over here. Oh, let's do it in red. So this is 1. This is pi over 2. This point over here, before it was minus pi over 2, comma, minus 1. Now it'll switch and it'll be over here. It'll be minus 1 comma minus pi over 2. And it ends up going like this. It's kind of a not so great version, but it should look like this. And you can kind of see that, right? Because in this left graph, you know, it's kind of approaching this 1, right? And so this one's also sort of approaching this 1. You can kind of sort of see it. So this is what's called, this would be the graph of the inverse of sine, and this is called arc sine, which if I could spell, is, so there's two ways of writing this. The two common ways of writing this are just arc sine of x, just kind of a long thing to write. But people also write sine inverse of x, right? So this is the inverse of sine. Okay. And it has the same sort of properties that the log had. It, you know, it has the property that if I take sine of sine inverse of x, that's just x. And if I do it the other way as well, it undoes sines. With a small caveat, right? We had to do this sort of erasing property. I wrote the same thing twice, didn't I? right? But this only holds, well, so let's see, the first one, so the second one only holds when, well, I guess the point here is that the domain of arcsine is, instead of being everything, it's -1 to 1. And so the only things you can plug into an arcsine are -1 to 1. And I guess I can use square brackets here. Okay. So mainly I want you to be aware of its existence, and I want you to know that this property holds. You know, if you have to use these on an exam or something, I'll likely give you like the definition and like its domain and stuff. So it's worth like looking at these in the book. So I kind of copied the tables from the book. There's one of these for each of the trig functions, you know, and they're all kind of a little bit different. So we talked about arcsine, right? And, you know, it's sort of like a similar thing we had with the exponential, you know, saying arcsine of x is equal to y is the same as, if you do sine of both sides, is the same as saying sine of what is x, okay? And here they're saying that the output here has to be between -π/2 and π/2. Kind of the other important one, so the ones I'd like you to know most well are arcsine, arccosine, and arctangent. So let's take a minute and think about arctangent. So like, what does the original graph of tangent look like? It looks something roughly like this, right? Let's do that in red. So tangent itself looks roughly like this, and it has these vertical asymptotes here. Where this is π/2, and this is -π/2. And so what this picture does is and then of course arctangent actually repeats itself many times. But we erase those because we need to make it 1 to 1. So we only take this middle part, and then we flip it over the line y equals x, and we end up with this picture. Okay. So arctangent is this kind of funny looking snake thing. Okay. And it's interesting because, you know, the domain of arctangent is what would have been the range of tangent, which is everything. So you can plug anything into an arctangent. No, you can't plug anything into a tangent, but you can plug anything into an arctangent. Okay. So let's do a couple quick examples here. Let's just think about how we would compute some basic things. So if I like take sine inverse of 1, or arcsine of 1. Now this is very similar to what you were doing with logarithms, right? When I was asking you for a log base a of x, I was basically asking, you know, e to what power is x, and or you know, a to what power is x. Here I'm asking basically you know, when you're trying to take the arcsine of something, you're asking the question, sine of what equals 1. So these are kind of equivalent statements as well. So can anybody give me a value for which sine is 1? An angle?
90 degrees.
Yeah, what's that in radians?
Pi/2.
Yeah. So in this class, we're going to always use radians. And there's a good reason that, because the formulas are different in radians and degrees for derivatives, and you'll be off by like this factor of 180. So yeah, so sine of pi over 2 is 1. So this is equal to pi over 2. Okay. And the only thing you have to worry about is, you know, was your y actually in the place it says it should be? Yes, it is, right? Let's think about another one. What about tangent inverse or arctangent of minus root 3? So this is asking the question, tangent of what is minus root 3? Okay. And that one's a little more difficult, right? But the way I think of it is, you know, tangent is sine over cosine. And so the only way this is going to happen is if I have a root 3 over 2 on the top and a 1/2 on the bottom. And then one of these has to have a negative sign, right? To end up with the negative. So what angle, and you have to remember that we're only looking for angles between minus pi over 2 and pi over 2, right? That's kind of the tricky bit with inverse trig functions, is which angles are actually allowed. And it's only the part that is 1-to-1 in the original graph. So what angle between minus pi over 2 and pi over 2 has sine root 3 over 2 cosine 1/2 and one of the two with a negative sign? So you might have to think about like the unit circle here. So we said we're only caring about the part that's between pi over 2 and minus pi over 2, right? So this part. And we need one of the two to be negative, so it has to be in this lower quadrant, right? Because that one, because in the first quadrant, both things are positive, right? And the one that has the sign will be the one where the y value is farther away. So it'll be this angle. And so this is minus pi over 3. So tangent of minus pi over 3 is negative root 3. Because the sine of pi over 3 is root 3 over 2, cosine is 1/2. And, or sorry, negative pi over 3 is negative root 3 over 2. Okay. And so, yeah, that's the original answer, is that angle. Okay. So it's kind of just playing with the unit circle and understanding that when you're asked for the arc tangent or the arc anything, it's asking what angle in the original function would give you the thing that you were plugging in. Okay. So these can be kind of, they take some getting used to. And then I should show you an example of one other type of thing that can show up sometimes. I was hoping to have you have time to practice this, but I don't think we'll have any. So I'll just show you one. So what if I take a trig function of an arc trig function? So something like this. And so here's where the SOH-CAH-TOA stuff can be helpful. Right? You guys all remember that sort of thing where, you know, secant and sine and cosine and tangent all have definitions in terms of sides of a triangle, right? Like sine is opposite over hypotenuse in a right triangle. And so what we're saying is here is we're interested in secant, or maybe let's do a simpler one first. Probably only have time for one. So let's do one that you can actually understand. Let's do sine of cosine inverse, because these are a little simpler. And we'll just leave it as an x of an x. Right, so here sine we're going to think of in terms of a triangle. So there's some triangle, some right triangle, where this part here we're thinking of as the angle. So I'm going to think of this as being cosine inverse of x. It's just some number that happens to be equal to arc cosine of x. And what we know about it is so like if I take cosine of theta, that's adjacent over hypotenuse, right? But what is theta here? The angle here is this arc cosine. Right, so that should just be x. Because remember, arc functions are the inverse, so it undoes each other. So what this is saying is that this should just be x. Adjacent over hypotenuse should be x. So I need to somehow come up with a triangle where adjacent over hypotenuse is just x. So maybe I do x over 1, because x divided by 1 is just x, right? Okay, but then I can fill in the sides of the triangle using the Pythagorean theorem, right? Like, it would say that x squared plus something squared is 1, right? And so this part, it ends up having to be like this. So this ends up being like this. Okay, so you guys all with me so far? Okay, so that was all just writing down a triangle with arc cosine of x. Now we're taking the sine of this angle. So sine is now opposite over hypotenuse. And that is, so the opposite is the square root thing. And the hypotenuse is just 1. So this ends up being this funny thing here. It's kind of strange how it works, but it works. All right, so any questions about that? I think we're about out of time for today. All right, well, thank you all for showing up. I'm going to go make a cup of tea, but I'll be sticking around here to answer questions for the next hour or so if you would like to get started on your homework. If not, have a good day, and I'll see you tomorrow. All right, take care.
Thank you.